Hello, today we're going to look at capacitors in parallel and in series and how they hold and store a charge. We've got effectively two circuits on the breadboard here. This first one is a parallel circuit, that's this circuit here. Parallel simply means current has more than one path to ground. The other circuit is a series circuit which has exactly the same three capacitors, but this time they're in series with each other. What we're going to do first of all is we're going to connect up the parallel circuit with a lower value resistor, and we're going to connect the power supply, and we've got two voltmeters, one on the power supply itself here and another one across the LED. And when we connect up the power supply, what we will see is that we have the LED comes on here, and the voltmeter LED has a voltage across it of 3.04 volts, and the power supply has a voltage of 9.9 volts. When we disconnect the power supply here, we're going to see that this voltage drops until it equals the LED voltage. That will be the capacitors discharging, and at that point the LED will no longer glow. So as we disconnect it, we see this voltage drops rapidly, and the LED, just about see that now, still lit, and we can see that the voltage at this point and this point are virtually equal, which means there's no potential difference across the resistor, which means no current flows through the resistor, and therefore the LED won't light. The capacitors will retain this charge indefinitely. If I was to remove both of the voltmeters, they would retain 2.4 volts indefinitely until we find some way to discharge them, usually by shorting them out across their terminals there. So that just goes to prove that a capacitor holds a charge until it has an opportunity to discharge. We're going to remove this 820 ohm resistor and replace it with one which is about 5 times larger. We will set up the voltmeters in the same way. And we will see the same type of result as soon as we plug it in. Capacitors charge up almost immediately to the power supply because there is no resistance in series. But when we disconnect the power supply this time, we're going to see that this voltage here drops a lot more slowly, and we're going to count it this time. So ready?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21.
22, 23, 24, 25. Boring, boring. Anyway, you get the idea. The reason it's discharging a lot more slowly is because the resistor, this resistor, is a lot larger, so it allows less current from the capacitors to discharge through the LED here. We're now going to look at the same circuit. We're not going to use the 820 ohm resistor, we're going to use a 4.7k resistor here. So we're going to do the same type of thing. Here we have a ground. We'll swap out the resistors. So this is effectively exactly the same experiment, except we have the capacitors in series this time. There we are. Hope it works. Here we go. So we're gonna plug the power supply in. LED lights, just as before. Same situation. Capacitors charge up, and we have the voltage across the LED. But when we disconnect the power supply, 1, 2, 3, 4, we note that it discharges much more quickly. Let's just do that again. It discharges to virtually nothing, mainly because of the way the resistors are set up. So as we disconnect it, it discharges much faster than it does for the parallel circuit. And that's because when we get on to do the maths, you will see that when you have 3 capacitors in series, if they're all the same value, the total capacitance is actually, if we've got 3, 1/3 of 330 microfarads. If we had 4 of them, it would be 1/4 or 1/4 of 330 microfarads. However, when they're in parallel, their values add. So we have 330 times 3. In direct comparison, this circuit can store 9 times more charge than this circuit.